All right, and now we have a talk from Turgut, Reis, Kursun, Jens van der Plas, Quentin, Stiévenart, Coen de Roover on a research paper on RacketLogger, logging and visualizing changes in DrRacket. Turgut, you have the stream.
Yes, thank you. So I'll be presenting, and so I think I have to share my screen. You guys can hear me, right? Can you hear me?
Yes, I can hear you well.
Okay, so I'm going to share my screen.
Yes, we can hear you on the stream.
And you can also see my screen, I believe.
I can see it.
Yes.
How about Porto?
Okay. All right, before we get started, just 1 second. All right. So welcome to my presentation. You can see the first slide, I believe. I just want to make sure.
I can see it okay.
Okay, thank you. Welcome to my presentation. I'll be presenting you a research paper about logging and visualizing changes in DrRacket. Here you can see the researchers behind this paper, myself, Jens, Quentin, and also Professor de Roover. So logging and visualizing changes. I will start by explaining what we mean by logging changes. So when we say changes, we refer to any interaction between the programmer and the IDE. So this could, for example, be the insertion of a line of code. And when we say logging, we're talking about persistently storing these changes in memory. To give you a bit of an example, you can consider the programmer in an IDE writing in some Java file. And once he's done, he can find all of his interactions back in some XML file, right? So he can see, I inserted some code, I deleted some code, I saved the file, opened the file, such things. The software that does this for you, that automatically logs your interactions, are called change loggers. Okay. Change loggers are often built as IDE plugins. And in fact, many change loggers already exist. They exist for popular IDEs such as Eclipse and IntelliJ and many others, such as Visual Studio Code, but there exists no change logger for DrRacket. And this is really where our research focused on. So the goals we had were twofold. First, we wanted to develop a change logging plugin for the DrRacket IDE. We named our plugin RacketLogger. And second, we wanted to evaluate the usefulness of our plugin by building a tool, a visualizer on top of it. Okay. So I'll give you a more and then delete it. Okay. And these interactions correspond with a certain log file, and here you can see it. Notice the insertion and the deletion of the code can be found back here. And also saving and closing the file can also be found. And this is essentially what RacketLogger does for you. RacketLogger really logs a hierarchy of changes. So I've already shown you the insertion and the deletion of code, which is a textual change, of course. And then we have the interactions. I've shown you the saving and the closing of the file, but we also log a change when files are opened. And lastly, there's a change logged whenever the code comes to a parsable state. So this means that the code is well structured in the sense that it can be parsed into a tree. This change is useful because it enables a richer way of logging, and I will come to that in a second, right now. So I've shown you so far the textual logs, remember this example, but there is in fact a second way of logging these changes that is richer in some sense. I'll explain that in a second. And in this way, we log changes as abstract syntax tree operations on the AST of the program. So here, you can see the code in the root nodes of the AST. Essentially, if you look at the node, you will notice that just this tree has been removed. So it's just a text deletion of the tree. But if you look at the same change as node operations, you can notice that this node here has been deleted, indicated in red. And this node has been updated in the new AST, and that is indicated in blue. In fact, there are three types of changes: node deletions, node updates, and also node insertions, which happen at the new AST. But in this example, there is no such node insertion. But in this one there is, so you can see it indicated here in green. This is a more involved example, and the point of the example is to show you why AST changes are interesting. So with AST changes, we can really tell how the structure of the code has changed. We can notice that the code really has changed around this subtree right here. And for example, we can also tell which subtrees have not been touched. And this is really interesting because if you have an expensive static analyzer and you notice that some subtree has not changed, you don't need to, you might not want to compute it again, and you can just use the result that you had for the previous version of the code. Okay. Now I want to tell you a little bit more about how you can capture these AST changes. So there are many algorithms that do this, and they often need three inputs. You need the textual changes, the old AST and the new AST, and then the algorithm will find the AST changes for you. Notice here the dependency of the AST changes on the textual changes. So you really need them to find the other one. And so that is why we log the textual changes in the first place. We, in our research, adapted an algorithm for scheme such that AST changes can be logged for scheme programs. I'll try to explain you the algorithm in a simple way. And essentially, the algorithm has to compare ASTs. But for a second now, let's think about comparing images, because that's more intuitive and that really tells you the essence of the algorithm. We have to consider one image to be the old image and then the other one to be the new one. Okay. What the algorithm does is it will start by looking for things that are the same. So for example, this left top corner, left top window is the same in both images. In that case, the algorithm notices it and knows that no node operations have to be generated for that window. And then once that's done, it will look for things that are different. For example, you can notice this doorknob is removed in the new image. Something that is being removed can only be found in the old image. And so you know that this is, in fact, something that's been removed. In contrast, something that has been added can only be found in the new image, right? And lastly, when something is updated, it will be you can find it in both images, but of course it will have a different form. And this reasoning that I just applied on the image translates very well to trees. So the algorithm will just look for nodes in the tree. For example, this white one represents one that hasn't changed between the two versions of the code. And so this means really that no node operation must be generated for it. Once that's done, it will look for nodes that are only present in the old AST. That means that that node has been deleted, and thus a node deletion operation is generated. Next, it will look for additions, node insert operations. And so just like this thing here, the node will only be present in the new AST. And so a node insertion is generated. And lastly, the same thing is being done for the node update. It's present in both ASTs, but the content of the node will be different. Here's the pseudocode of the algorithm that we have used for building our plugin. And in gray, we have highlighted parts of the algorithm that we have adapted, and I will focus on them. So our contributions to the algorithm. The adaptations were made because we wanted to fit the algorithm more tightly with scheme, with the syntax of scheme expressions. So the first change that we made was thoroughly checking whether a node is affected by a textual change. So we noticed no other research paper on this subject was elaborating on some on when a textual change affects a node, when exactly, and not in as much detail as we have. And so we really try to find some cases that weren't discussed anywhere else. Here, I'll give you a few examples, and I hope that makes it clear. Consider this node here, and consider then adding a y just next to it. In that case, they will be considered as two separate expressions. So this textual change here is not affecting this node. Okay. But if this node had a different form, if it were just an identifier x, and then you added a y, it would be affected. So this entire thing would be seen as one identifier, one expression. Okay. And then if you didn't just add a y, but you added first a space and then a y, you would again have two expressions. So really, whether this node is affected by a change depends on the type of the node, whether it's an identifier or not, and also where you have spaces and new lines and so on. So we really try to identify as many edge cases as we could, and such edge cases result into the program being more accurate AST changes. The second adaptation we made is about update for ancestors. And here I invite you to look at these codes. So you can see nested begin expressions, and imagine that the second x is being removed. This corresponds to this old AST and this new AST. What we noticed is the original algorithm was not generating any update operations for the nodes that contain this x. So these x were contained by several begin expressions, but no update operation was being generated between these two, and so on. Although for scheme, that would make sense because the x is in fact contained by by the surrounding begin expressions, and thus whenever the x is changed, the surrounding expressions have also changed. So we decided to generate an update operation for every corresponding pair of ancestors. Now, finally, I will come to why change loggers are useful. So, as I said, we can log textual and AST changes. And the reason that we do this is to build other tools using these changes. So here you can see the application stack. We have the DrRacket IDE. On top of that, you can build, we have built RacketLogger, our change logger. And on top of that, you can build any tool that requires changes. And in fact, such tools that make use of changes have already been built, albeit with a different change logger than RacketLogger. So for example, some researchers have built a tool to analyze programmer behavior. And this is useful because then you can see the behavior of programmers in terms of productivity, development, and also how they go along with testing, for example. Another example is incremental analysis. And this is something that I kind of hinted towards a second ago. It's essentially static analysis that is made more efficient by looking at the changes to the program, to the AST changes, in fact, such that not the entire tree needs, such that we don't need to analyze the entire tree again whenever a change is made. And lastly, and this last example is something that we have built on top of RacketLogger, is an AST changes visualization. And here I want to show it to you. So this is, here you can see the DrRacket IDE with two plugins installed, RacketLogger that provides AST changes, and second, our visualizer that will use these AST changes to beautifully show the AST and the changes to it. So here you can see the programmer writing some code, and then the changes are immediately shown. And if you change to another tab, then the changes, the corresponding changes are immediately logged. Once we had our tool, we decided to evaluate our plugins. So we wanted to, we conducted a user study with 5 users, and they reported 9 hours of total usage. Their overall, their first impression has been positive. They found our plugins to be, our visualizer to be responsive, clear and useful, and they only found one minor bug, so it was rather reliable. Of course, the study is small, but maybe in the future we can build other tools on top of RacketLogger and do other studies as well. So in short, what have we achieved? We built the first changelogger for the DrRacket IDE. As I mentioned, changeloggers exist, but they exist for other IDEs. Our changelogger captures both textual and AST changes. Recall that AST changes are a richer source of information because they tell you exactly how the structure of the code has changed. And lastly, I've argued that this our changelogger is useful because we can build other tools with it. And I've shown you the tool that we have built, the AST visualization tool. And we did a user study, as I've mentioned, that was positively received. Thank you for listening.
All right, thank you, Turgut. So let's see if we have some questions, whether from the in-person audience or from the chat.
We have a question from the live audience. Who?
So my question goes like, is this tool really tied up to DrRacket, or is there any possibility to extract some common code to adapt it to other editors?
So the algorithm that we have adapted is actually meant to be a more general approach. And so if you look at the algorithms as an abstract thing, then yes, that's possible. And you can, for example, use the same algorithm for other languages such as Scala or Java. But the tool that we have implemented, of course, that is tied up to DrRacket. In short, the ideas are generic, but our tool that we have implemented is for DrRacket.
You said that the users generally positively evaluated the use of the tool. And was it in any way clear what was basically, well, the ratio of value of just having a live updated AST at all and of seeing specific changes?
So what exactly do you mean by the ratio? I don't think I understand.
Well, I mean, you gave the users, well, some new functionality which has a lot of parts. That first of all, they see the syntax tree in the real time, and then also the updates are highlighted. And did the users like say anything in the free form how they were using it and how clear it was? What was the core part? Was it just the tree more valuable, or there was specific value in changes being highlighted too?
I would say that I would say that I remember our study was asking many questions on the Likert scale. And if I remember correctly, our users found both the AST useful, but also the changes. So, and I think the changes mainly were useful for navigation purposes. So once you know, you can tell where exactly the code changed. And so if you forgot, for example, what looked my last version of the code, last parsable version of the code, then you could always see it on the visualization. So I would say yes. I would say both the AST, the fact that the AST was shown was useful, but I would place the highlights as more important.
We have an online question. It says, is the tool available as a DrRacket package?
It's not. It's not yet, at least.
Okay, I have a question. A couple of years ago, we published an ELS paper on incrementally reading buffer in second climax using an incremental common Lisp reader. I actually think that this approach that we had would take care of all of the edge cases that you were citing before, where the addition either impacted or did not impact the preceding expression. So have you looked into that algorithm of ours? I believe it takes care of everything from the root down. So you might have a look at that.
Yes, indeed. I sure will.
I forget the name of the paper, I'm sorry.
There is one more question from the online world. Why are text changes required to compute the AST changes? Is that just a remnant of the original algorithm
we used, it isn't really meant to be just for Java. I think they apply it to Java, but really their idea is to make it possible to use it for other languages such as Scheme, and that's exactly what we have done. And the textual changes, in fact, that algorithm needs it, the one that we use needs it, but other algorithms that use pretty much a totally different approach also use these textual changes. So I would say that for most, at least the ones that I know of, these algorithms always use the textual changes in order to compute the AST changes. So yes, there's a dependency.
Okay, thank you. Anything more from the audience in Porto?
No, everyone's happy.
Okay, so I guess that's all.
All right, thank you.
Thank you.
Thank you for